2, 4 on the first equation. X2 prime is 5x1 minus 1x2. Right. So you can check it out. AX would be equal to 2, 4, 5, negative 1 times x1, x2. And then check it by matrix, multiplication by this matrix by a column vector. We get 2x1 plus 4x2. And since this is a 2 by 2 matrix multiplied by a 2 by 1, you can think of a vector as a 2 by 1 matrix. And since those match, they can multiply the number of columns of this one and the rows of this one. And the result will be a 2 by 1. And the other equation, 5x1 minus 1x2. Right. So that's AX, and that was equal to our x1, x2 prime, right? x1 prime, x2 prime. Okay. So we can read it this way. For these two vectors to be equivalent, this component has to be equal back equivalent. Well, that's the first equation in the system. This is the second equation in the system. Okay. All right. I'm going to skip number 3 just for the sake of time, but number 4, let's look at some of these things. So, first off, the determinant of that matrix, this notation.
The absolute value bar does not mean.
It does not mean absolute value in the same way as it's absolute value of a single number.
Magnitude? It's not magnitude either.
Not so much. Determinant.
This new operator.
Yeah, I usually write it like this: DET, determinant of A, and determinant operator takes in a matrix, spits out a real number. Okay? And if it's a 2 by 2 matrix, how do we find that determinant?
A, C times B, yeah.
Right. Product of the main diagonal minus the product of the off diagonal. So we get 6 minus 4, we get 2. Okay, so it's non-zero. That's going to be special. Non-zero determinant means it's what? Non-singular. It has a determinant, so this matrix would have an inverse. Does not equal 0. So A inverse exists. You could say it's an invertible matrix. Okay, we're not going to talk so much about finding inverses and things like that. We're just going to kind of use what we need in this class. All right.
Different A and goes up there.
Yeah, oh yeah. Yeah, it's a different one. So this is a new A, right? This is number 4. All right. So A minus 3I. What does 3I look like? Right. And if we're talking about a 2 by 2 matrix, the identity matrix of the same order is 1, 0, 0, 1. So a scalar multiple of a matrix, multiply each entry by that scalar. So all the off diagonal entries remain 0, and all the diagonal entries are just scaled by 3. All right. So what would A minus 3I look like? So A 2413 minus 3I 3003, and subtraction. If you know how to add two things, you know how to subtract, because subtraction is defined as plus and -1 times that matrix, right? And we know what a -1 scalar multiple looks like. So essentially, I could use real number subtraction and subtract corresponding components. So entry 1, 1 minus entry 1, 1, and we get -1. 4 minus 0 is 4. 1 minus 0 is 1, 3 minus 3 is 0, so that entry got knocked out. All right. All right, oh, determinant of a minus 3I. Okay, again, with the notation, DET, determinant a minus 3I, same thing. All right, well, we got a 2 by 2 matrix, so its determinant is just product of the diagonal, 0 minus product of the off diagonal. Non-zero determinant there as well. Okay. All right, and how about this guy? D. So that's the Greek, what's that one, lambda? Lambda. It just reminds me of what, Revenge of the Nerds. I'm an old movie buff, they just stick it in my head. Revenge of the Nerds, the original one, they're lambda. Okay. All right, so part D says find a minus lambda I. Well, from what we saw before, well, a is just going to be 2, 4, 1, 3. But what does lambda I look like?
It's just the identity matrix.
With lambdas, right, it's scaled by lambda, so it's going to be lambda, 0, 0, lambda. Okay? All right, so what does this matrix look like? 2 minus lambda in that position. It's just component-wise subtraction. 4 minus 0, 1 minus 0, and 3 minus lambda. Okay? There we go. All right, building up. Part E says, oh, find the determinant of that matrix. Leaving the answer in terms of lambda. These are going to have some special meaning. Okay? These values, lambda, that we're looking for, they are going to be called eigenvalues. Eigenvalues.
Eigenvalue.
Eigen.
I mean, it's not like Botticelli or something.
No, it's German. Right? Eigenvalues. They say something about that. It means characteristic, although I don't know how they translate that literally to the word characteristic. But anyway, I like to keep those factored. The determinant would be the product of the diagonal, so I'm going to have 2 minus lambda times 3 minus lambda minus 4. Right? Foiling this out, we'll have 6. I'm going to put that at the back, minus 4, just for the sake of time. 6 minus 4, I'm going to have 2 with the last entry, but then I got minus 2 lambda, minus 3 lambda, that's minus 5 lambda, and lambda squared. All right. Sometimes in linear algebra, I think this is called the characteristic polynomial. It's a polynomial involving lambda. Okay? Big deal right now. Okay. All right. Oh, solve the equation determinant a minus lambda I equals 0. We got lambda squared minus 5 lambda plus 2 equals 0. In other words, we're finding the values of lambda that make this determinant, or this matrix, have a 0 determinant. Okay? All right, and that's not going to factor.
Not very
Yeah.
well.
Not well.
Does it? I don't know.
No, it doesn't.
Two having factors that equal 5.
Well, no, but like you could set the 2 minus lambda and 3 minus lambda equal to 4.
I plug it into the calculator.
Oh, then you're making...
I got root 17 plus 5 all over 2.
Yeah, you're going to get 5 plus or minus square root b squared, that's 25, minus 4 times a times c. This is just like a polynomial, it's just like a quadratic formula in x, except then we're calling it lambda, so that minus 4 times a times c.
That's so hopeful.
All over 2 times a.
What?
All right, so we get 5 plus or minus, that's 8, so what's that, 17, root 17 over 2. Yeah, those are what are called the eigenvalues of that, of the associated with matrix A. All right, we'll get there though. Okay, so that's just an exercise in some matrix operations, things like that. Okay. Yeah.
So the eigenvalue is effectively the matrix like flippable.
Well, it makes it
Because if it equals 0, you said it would be.
right. Then it's it's singular. I always get the definition of singular mixed up. If the determinant is 0, it is singular.
Okay.
It does not have an inverse.
Oh,
But shouldn't there be other values besides the 0 value, which would make the determinant equal to 0? The ones that are like the, I guess what they call the inverses of the other two values? Oh no, because those ones are just,
Right. 2 by 2.
it has to be equal to 4, right? Not equal to, for the,
This would have to equal 4. Yeah, but same.
oh, that's what you did. You already put the 4 over there. Sorry.
Mhm. Okay. All right, let's get back started into 5.1. So, systems. All right. So, as an example, let's start by looking at this system. X1 prime equals 3x1 minus x2. And the other one, x2 prime, equals 5x1 minus 3x2. Okay. And everywhere in here, the prime notation that they use, these are all dependent variables. x1, x2 are actually functions of t. So the prime notation means derivative with respect to t. Okay. So x1 and x2 are actually dependent variables in this system. All right. So what we can do, we got a little bit of practice with this. We can write this system in matrix form. How?
X1, X2 prime as a vector.
Right. So x1 prime, x2 prime, that would be a single vector. And a quick reminder of vectors. Now, a lot of times you see them like this, right? I'm going to call it x1 of t, x2 of t, something like this. Of course, we can write this as a column vector. It's the same thing. This is the way we sort of view it. For some reason, linear algebra, this is the norm to see it like that. Now, if you differentiate this, and if this is a vector function, if you called it r or something, then the derivative of it is just the derivative of each component. That's one thing to note. So if I take the derivative of a vector function, it's literally just x1 prime of t, x2 prime of t. Okay? So same thing with a vector valued matrix. The derivative of that matrix would just be each element, the derivative of that entry. Okay? All right, so we can write it this way. And the reason, the big reason we write things in, especially 2 by 2 getting bigger, 3 by 3 systems, is just the sheer volume of stuff you'd have to write otherwise. So we write it with vectors. So x prime equals p x. Okay? I'm going to call that equation 1. So I underline, or I put a bar over my column vectors just to distinguish them from a single function x of t.
Is that like an arrow vector? Like
It's kind of, yeah, it is. Yeah. All right. So in the book, those are all bold. They just do it bold.
Gotcha.
Mm-hmm. All right, where P would be what matrix? P would be, we call that the matrix, the coefficient matrix. What would it be? Mm-hmm. Yeah, 3, -1, 5, -3. And of course, I'm taking this x bar just to represent x1, x2 as a column vector. Okay? All right, but what we're really, just to remind you, that these are functions of t in each of these positions. So to remind you, this is x1 of t, x2 of t. We're seeking solutions to a differential equation as a function, so that's what we're looking for. All right, so this is a column vector, and this is a 2x2 matrix. All right, and look at how compact that matrix equation is. All right. So one thing we can do, we're not solving this one yet, but verify. So verify that x1, and this is where the notation gets nasty, one solution, x1 bar. So this represents one particular solution of this system. So x1, this contains an x1 and x2 equals, say, e to the 2t 1, 1, and x sub 2 equals e to the negative 2t 1, 5 are solutions. To equation 1. Now, one other way we can write this, e to the 2t, for any value of t, that's a scalar quantity. So you can write this as e to the 2t multiplying by this, e to the 2t. And this one could be written as e to the negative 2t, 5, e to the negative 2t. Okay, so we want to verify that those are both solutions to equation 1. All right. So how would we do that?
We plug them in for
Plug them in.
for each times it, right?
Right. So let's look at the first one, x1, first. Let's look at that. What would be its derivative?
2 e to the 2t.
2
So the way the book often writes it, d dt of the, this is a vector function x, and we do it component-wise. So I'm not going to keep this notation up, but I can think of it as e to the 2t, e to the 2t. We're taking the derivative of each component is how we find that. And we get, that's a derivative prime. Yeah, 2e to the 2t, 2e to the 2t. All right, so that's x prime. And let's see if that's equal to p times x. So px, again, that matrix P was 3, negative 1, 5, negative 3. x1, we're saying that this is a solution, e to the 2t, e to the 2t. What does this equal? That's a 3. It would be 3e to the 2t minus 1e to the 2t, right? All right, and the second component would be second row and times this column, dot product, 5e to the 2t minus 3e to the 2t. And if we simplify that, we notice that I got e to the 2t, so that gives me what? 2e to the 2t, 2e to the 2t, which is exactly equal to x1 prime, which is what we wanted to show. x1 prime equals px1. Okay. All right, let's do the other one. So for the other solution to that system, which does contain both functions x1 of t, x2 of t. So for this guy, x2 prime this guy's derivative, right? What would be the derivative of x2? Negative 2e to the negative 2t, negative 10 e to the negative 2t. Right? Okay. And let's just check out that it does solve the equation in 1, px equals, and let's write down p again just so I have it, 3, negative 1, 5, negative 3, times x2, that matrix, or that vector x2 is e to the negative 2t, 5 e to the negative 2t. Okay, and this is multiplication of a 2 by 2 matrix by a vector, a column vector function. It's a vector function. Okay. All right, and the way we do this is dot product, row 1, column 1. So I get 3 e to the negative 2t minus 5 e to the negative 2t. And the second entry, 2, 1, row 2 times column 1, 5 e to the negative 2t minus 15 e to the negative 2t. And if we combine those terms, those are both e to the negative 2t terms. 3 minus 5 gives me negative 2 e to the negative 2t and negative 10 e to the negative 2t. And this, sure enough, is that equal to x2 prime? And that's what we wanted to show. x2 prime equals px2. So both of those vector functions solve it. Okay? Run off the page. All right, now, interestingly, a lot of the results from chapter 3 that we saw, or was it 4? I'm getting so lost now. 4, 3, 4. Oh, we just did 4.1. We skipped it. Yeah, we didn't do the rest. So in chapter 3, we talked about single differential equations, and if I have linearly independent solutions, then any linear combination of them is also a solution. The same thing holds with a system